Welcome to the optical communication course. So today we will see the model 4 in which coupling and receiver operations we will see. So model 4 itself is saying there is the two types, two part of this model here. One is about a coupling a power and a receiver operation. So coupling power means what? From the source power will be launched and that power launching and that power coupled to the source. So in which we will learn that how your power will be launching the power. Then we will learn that a coupler, and in between that a fiber we will learn that splicing technique. So already we have learned that coupling and splicing and launching, power launching somewhere in a last model. Okay, so we'll go again briefly regarding that how power launching is there and how coupling and splicing will be there. Okay, that is about a part one. Then a part two, it consists of a optical receiver operation. So in this particular uh, part 2 we learn that how your receiver operation work here. What about the various types of amplifier? Because in a receiver we say that we have a detector and signal falls on this particular detector, and then how we are getting this signal, it will that photon of a light will fall on this detector, then it will generate a current pulse. Then how we are getting this particular current pulse? Because photon will convert a current, then we need to amplify that particular current. So here after detector we have in a receiver, we have a amplifier or a pre-amplifier. So what are the various types of that pre-amplifier used in this particular receiver operation that we will learn. So here the receiver operation that is important because we say that a detector will detect a photon of energy. So how much photon of energy need to be fall on this detector, then and then it will generate a required current pulse. Again I am saying word required. Why? Because your circuit, your amplifier amplify that particular current pulse. If supposed to be that current pulse level is not large, so means it has some noise. So again in amplifier that noise will amplify there. So that's why that detector detect the lowest possible photon of energy, but it will produce a current pulse with a low noise. So now what are the various noise in this particular detector that we will learn in this receiver operation, and what are the various amplifiers, and what will be the eye diagram means at what particular location of period that signal is to be detected there, that we will learn. So now we go one by one. We start with a power launching and a power coupling. So when we say that a power launching and a coupling, so power launching means from source to fiber. Okay, we say that a power launching is from a source to fiber. Now here we can say that what type of a source we have, and then how your power will be coupled to the given particular fiber. That is about a power coupling from the source to fiber. So now we say that supposed to be we have a light emitting diode, LED is there. This is about a light emits from the light emitting diode. Okay, now this is about your source. It emits a radiate or it emits a photon of energy in all the given direction. Now the question arises here: what will be the intensity of that particular light? And then here we supposed to be consider a optical fiber, and how this whatever the light coming from this particular source, it will be launched inside the optical fiber. So now here we consider that what will be the emission pattern of this particular source. For a source, emission pattern is important because in which direction we have to connect, keep our optical fiber, so that will give the place or a position to connect your fiber there. So that's why we need to know about the emission pattern. So in only one direction that source is emitting, we have seen that surface emitter and edge emitter, it has the highest intensity in a one direction. But we have seen that from a receiver point of view, or from our point, our viewing point, if we see, so that source is emitting the light in all the directions. But it's not true, because it has a intensity in only one direction, maximum intensity in a one direction. So where is the maximum intensity of this particular source, that is to be identified? Then we have to keep your fiber, optical fiber, near to the particular place there. So then from that we can find out how much will be the coupling efficiency. Then coupling efficiency is nothing but what will be the power emitted from the source, and that will be coupled into the optical fiber. So that will give us the coupling efficiency. So this one is about a power coupled into the optical fiber, and this one is the power coupled from the source or emitted from the source. So this is about a coupling into, and this is about a power emitted from the light source. So that will give us the efficiency. So now we say that a power launching inside the fiber, so it is depending upon that what type of fiber we are using. So that's why we should know that a various coupling mechanism. So now we say that a source and fiber that will be on axis. Okay, now if that radiation pattern will be large, okay, emerging area, emitted area will be large, then we need to use in between that fiber and a source some coupling mechanism. And that coupling mechanism is nothing but what, some types of a lens is to be used to improve the coupling. So now whether we wanted to use a lens or not, it is depending upon that what will be the type of a source and what will be the type of a fiber there. Then in between this we say we use a source, that is the lens here. But some of the sources, that laser or LED, they manufactured with their optical fiber. They have a small fly lead. So we have seen that a surface emitter, small optical fiber portion is there, and that is inbuilt at the time of manufacturing of a given particular source. So that fiber is there inbuilt. Now then, source and a fiber is there inbuilt. Then we need to join it to fiber, because source has small fiber, and that fiber is to be coupled to the external fiber. Then we need a fiber to fiber coupler. So now what are the various type of fiber to fiber couplers required? Then we will learn here. Then when we connect a fiber, or when we launch a power from one, from source to the fiber, so in that case we need to consider that what will be the core size of a fiber. Even if it has a fiber here with the source, then we need to consider that what will be the core size of the fiber there. And then we should know that what will be the co-refractive index of the particular given fiber. Now, if supposed to be we are connecting it to fiber, then end of the fiber is to be a smooth. If that ends are smooth, then and then we are able to connect it to fiber. So then, if that ends are not smooth, then we are not able to connect it to fiber. So then, what happen? So there may be a loss of a light will occur. And again, when we connect it to fiber, we need to consider that that is about their axis is to be matched. Core is to be matched. Okay, right? This one is about the core of the fiber is to be matched. Along with that, their axis is to be matched. Then we connect it. This one is about your front side that is to be matched. That is to be seen. So that is about a part we can say that when we connect it, couple a two fiber there. So this one is about your we say a power launching and a coupling operation. Now we will consider that for a given particular source how your power launches inside the optical fiber. So we should know that what will be the emission pattern of a source. Generally, we express that emission pattern or a source output pattern in a spherical coordinate system. Now, if supposed to be we have the source that is about a light emitting diode, so this is nothing but the emitting area of the light emitting diode for the given particular source. Now, in this case, here we can say that emitting area center and this is about the emitting area of LED. Now, in this particular case, if you see that for a given particular emitting area, we have the angle phi, and then we say that that perpendicular to this particular line, it makes an angle theta here, and this one is nothing but the R here. So, if we consider that a surface emitting LED, and that for a given surface emitting LED, the output pattern is Lambertian pattern. Output pattern is a Lambertian pattern, or you can say that Lambertian output pattern. Okay, Lambertian output pattern. So in this case, whatever the power delivered at an angle theta, that will be measured in terms of a whatever the relative emitting area, and that depends upon the what will be the angle theta normal to this emitting area. So we can express that the emission of a Lambertian pattern that will be of what a b of theta comma phi is equal to b0 cos of theta. So this theta is nothing but what? That is the projected area in this emitting area, that is angle in this projected area, and then we can say that the emission pattern or the radiation in this particular theta and phi or radiance is nothing but bit of theta comma phi. So this is about the radiance along to the normal to the radiating surface. This is about a radiating surface. This is some normal here. And a cos of theta, that is about the viewing direction. Now, if you see that radiation pattern for the given source, so in this case, we will get that a radiation pattern of a source will be, we will get that in the given direction, it will be a maximum. So likewise, this one is about the radiation pattern of a source. But if you see the cos of theta function, sorry, now this is about a cos of theta function, and here we'll get that a maximum radiation in the given particular direction. So this is about a 0 degree, 10 degree, 20, 30, 40, 50, likewise. Means overall, if you calculate that, so this is about 0, 10, 20, 30, 40. So we have the radiation pattern for a light emitting diode, that is about a Lambertian pattern. And then how much is the power couple from this source to the fiber there? It is depending upon that what will be the brightness in the given direction there. So if we consider that a power couple into a fiber, optical fiber, or a source here, so in that case we should know that what will be the a fiber core is supposed to be, we say that this is nothing but a light emitting diode, or you can say that a active area of a light emitting diode. Now how your signal will couple, how your power will be launched inside the optical fiber. This one is about a core of a optical fiber. Active area, this one is about the core. Now from this, we say that here we have the, I think this one is a too long, I have drawn here. Draw it again. That will be nearer now. This one is about a core of your optical fiber, and this one is your active. Now from this particular active area, if you see that this one is about a radiation pattern. This one is about a radiation pattern of this source. Okay, this one is about a active area. This one is about a radiation. Now then, so the whichever the light coming from the source, that will be launched inside the fiber there. Now this particular region, here. This again a part of a radiation pattern of your source. But this light, whichever the light coming from the source, that is nothing but a loss because it will not propagating inside the fiber. But again, how it will propagating because a fiber has some particular numerical aperture area and then it will propagate the light inside the fiber. Now this one. Now this one we say it is about a core, a cladding. Now this one is a power is coupled inside the fiber. Now this area. So for a given particular fiber, we should know that what will be the numerical aperture or a acceptance angle. Now this one. Okay, here we can consider that this one is nothing but the acceptance angle of the given particular fiber. Here. Okay. And we say that this is about radiation and here we have the acceptance angle of the optical fiber. So this one is nothing but it will not propagating inside the fiber whichever the light because this one is not a part of the light here. So it will not even this one will be the radiation pattern. Only the signal from this given particular region that will be propagating to the fiber there. So we consider that optical power P we can write that will be in terms of what will be the emitting area of the given particular source and all. So that's why we can write in terms of what will be the given area that is DAS and this is about a solid angle of this particular optical radiation pattern and B of what will be the solid emission angle and a solid area. This is about what we can say a solid area and this is about we can say that a solid angle. Okay, there is nothing but the area and a solid emission angle of this particular source and then we can write this term that beta B here that is radiance in terms of a solid angle that is we can write in terms of theta and phi here. Okay, instead of this one we can write in terms of a theta and phi and then we'll get that term the power P is equal to what 0 to what we have the radius 0 to 2 pi and this one 0 to 2 pi and 0 to theta a b of theta comma phi sine of theta d theta d phi d theta and dr dr. Okay, so you know that this one in a spherical coordinate we have written. So we'll directly write that is sine of theta d theta. That will be what is sine square of theta because we have the solid angle theta a. So sine square theta and that sine square theta is nothing but the numerical aperture. So we can write here the equation is nothing but pi b 0 0 to rs to 0 to 2 pi numerical aperture square d theta s to r dr. Now if we consider that a source, if that source is a LED, okay, if that source is a LED and for the power for this particular source and we have the strip index fiber, then how much will be the power coupled inside the optical fiber? That will be depending upon that pi square r square e 0 na bracket square, or approximately we can write that is 2 pi square r square e 0 n1 square del here. Now, if this one is about the, if we consider that the power in terms of a strip index fiber. Now, if you consider that a power emitting from the source, that will be equal to what? A pi square rs square, that is the emitting from the source. Then in that case, we can express that above expression, that is power LED to step is equal to Ps Na square. But in that case, Rs is less than or equal to A. That is about the radius of the core of the optical fiber. So this one we will get that a power launching or coupling inside the optical fiber. If that radius of the emitting area, okay, if it is larger than the fiber core radius, only the power from the whichever the fractional area. Suppose now we can say that this area is larger than this optical fiber core, then a small fraction of the power will be coupled there. So that we can write in terms of what L step is equal to A by Rs bracket square Ps and Na bracket square. In that case, we can say that Rs is greater than the A here. So this is about a light emitting diode and its strip index fiber. Similarly, we can write a expression of what a light emitting diode and a graded index fiber. And that graded index fiber, I will write directly the equation is equal to pi square a square beta 0 Na. That Na is again depending upon that what type of a profile we are using, alpha by alpha. So this is about your power in LD. Now, if you compare this two equation, even if it is a strip index fiber or a graded index fiber, so in the all these equations, the common factor is about the numerical aperture. So what do you mean by this particular equation? Because for a given particular optical fiber source, even if the radiation is a large, but what happens? So power will be launched inside the fiber. It is depending upon that acceptance angle of the given particular fiber. So that acceptance angle is depending upon that. Say that it is a numerical aperture. So core size of a fiber will tell you how much will be the acceptance angle. This is about a acceptance angle of a fiber, and this is about a maximum acceptance angle that we have considered for the given particular fiber. Here is a common factor in this two expression, that is about a numerical aperture. So power or light coupled inside the optical fiber, it is depending upon that numerical aperture of a optical fiber, and that numerical aperture will changes based on the what will be the core size and what will be the refractive index of this particular core there. So that's why here somewhere we say that about the radius of the fiber that matters. So similarly, we need to know about that how much will be the power will be launched. So that is important here. So it is depending upon that what will be the acceptance of the particular fiber. Then we again say that a source and a fiber there is a gap. So that's why we should know that what will be the refractive index in between that particular source and your fiber. That is to be important here. So that is about your a power launching inside the optical fiber. And again, we need to know about that for a given particular source, how much will be the wavelength. Okay, that part that we have seen earlier in a model 1. So which wavelength is supposed to be propagating through the fiber, because if you consider that a gradient index fiber, then the number of modes and everything propagating through the fiber, that is depending upon the wavelength. And then again the fact, then one more factor will come, that is about the core of your optical fiber size. Okay, core size of optical fiber. If the core size is increases, the number of modes are increases. So that's why how which wavelength is supporting by this fiber, or what mode is supporting by this fiber, that is depending upon that wavelength, operating wavelength of a source. So we should know that what will be the source and what type of a fiber, because shape index and gradient index, okay, profile is different, the number of modes are different. And then other factor is to be considered, that is regarding the what will be the dispersion, because we say that for a multimode fiber there may be a intermodal dispersion, and we say that to avoid the intermodal dispersion we need to use a gradient index fiber, so that we can minimize the, not avoid, we can minimize the dispersion. So that is about one part. Another part is about we need to improve the uh, launching of a light inside the fiber, and for that improvement we required a lensing scheme. Okay, lensing scheme that will be required for a coupling improvement. So means we say that for a given particular source, it emits the light, okay, and we have a optical fiber that is to be used to connect directly to the source, or we have a fly lead here inbuilt, and then they will connect to the fiber. Now, what will be the emission area of this particular source, whether it is LED or laser now, then your coupling scheme will be different. But generally, what happen for a laser, light will be likewise. Okay, but if you consider that a LED, it is a broad one, spectrum will be broad. Okay, it emits in the all the divergence here. Okay, so for that purpose, from the source to the fiber, what are the various schemes to be used to couple the power inside the optical fiber? Few examples of a lensing scheme. In that case, we'll learn here. So this one is the light emitting diode, and it has a active area. So now we can use a fiber that will be a rounded shape. End. Okay. End of the fiber means here we are coupling the fiber, that coupling the power. So this one is about, we can say, core, and this one we say it is about a cladding. So that is about, we can say, we will use that rounded end. Okay. This one is about a rounded end so that more power will be coupled there. So because of the flattening surface here, so if it is a rounding one, so then what happen, large area getting by this particular round structure means whichever the light emitting from the source, they will get the large region. So that's why there may be improvement in the coupling of the light there. Another one is about non-imaging microsphere here. We have the of LED. This one is about the active region. Fiber we have. This one is about a cladding. This one is about a core. Here we can use a non-imaging microsphere. This one is about a non-imaging microsphere. So this one is a microsphere that is useful for the what? For a surface emitter. Okay, this one is useful for the surface emitter. So this lens is about a spherical lens, and it has a refractive index is larger than the whatever the refractive index of this outside medium, and this one it has a emitting area will be a circular in shape. So now whichever the light coming from this particular source, so that will be propagating through this particular spherical surface. So that's why for a given particular microsphere, okay, or we can say that is about a, we say, a small lens likewise, and that lens has some particular focal point. So we can say that whatever the emitting surface we say, so that will be located at the a focal point of the lens here. So now what do you mean by a focal point? Focal point means what? Just like for a some particular elliptical shape of a spherical shape, somewhere a center of that particular ellipse or somewhere up that circular shape. Supposed to be, this one is about a focal point. We say if supposed to be this focal point is the emitter, so it emit a light likewise. And we say that this is about a reflector, so it will be reflected. So a point here, all the incoming or outgoing signal, they have a simple one particular source there. That is about a focal point. So light travel from this particular lens there. So then because of that particular focal length, so it will radiate in the given particular direction. So that's why we can consider that various scheme, non-imaging sphere, or we have the, we can say that imaging sphere. Okay, likewise, that is about the various scheme we have to be used. So this is about a technique, so concentration of a power inside a given particular fiber from the source here. Then Another is about a cylindrical lens. Okay, this one is about a cylindrical lens. Then we have a spherical surface LED. Sorry, this one is about the active area. And for this active area, it has a spherical surface LED there. And then we have the spherical surface end here, fiber end. Likewise. So this one is about a spherical LED and a spherical ended fiber. Okay, they are about spherical surface. Or we can have a taper end, active region, or we have a about a core, and this one is about a cladding. It's about a taper end. So we can use a various technique to couple the power or a lensing scheme to improve the optical power so that your maximum power will be coupled inside the fiber. So that is about the lensing scheme here. Now this various scheme is to be used just like to couple the fiber, okay, couple the source to the fiber. Now then already we mentioned that there should be a specific acceptance angles and all so that whichever the numerical aperture of the fiber according to that power will be coupled. So that is about if we have a source and a fiber, so directly we can use the various in between medium so that your power may be improved. Okay, coupling power coupling to the fiber will be improved. So way of coupling the fiber. Next, we consider that in this model, so fiber to fiber joint. How your fiber are two fibers are joining together because we say that a power launching. Now we need to know about that fiber to fiber coupling. So to couple the two fiber, we should know that what will be the fiber to fiber coupling efficiency. Fiber to fiber coupling efficiency is equal to what will be the number of emitting modes